everyone. So welcome back to Game of Apps Coding Challenge. This week we have a very interesting problem, and today I have with me Ronald.
Hello. This week's problem was probably our most challenging yet. We saw probably the fewest amount of submissions, but for those of you that submitted, most of you did a really great job, so we're proud of you. But I think what's more important is to just go through some of the submissions and see some of the different approaches everyone took to get to the right answer.
Okay, great. Thank you, Ronald. So yeah, let's get to it. So this week's problem is, I guess I called it number of steps. And the idea was to find a sequence of numbers that add up to the target. Now, there were a few rules. So in the first step, you may take one step forwards or backwards. In the second step, you may take 2 steps forwards or backwards. And then each subsequent step, you would take either 3 steps forwards or backwards, and then 4 and so on until you hit the target number. So here's some examples. So if, let's say, the target was 1, then you would reach that in 1 step. You would take 1 step forward. If the target was 6, you would reach that in 3 steps. You would take 1 step, then 2 steps, and 3 steps. If the target was 5, you could take 1 step, 2 steps, 3 steps, 4 steps, and then move back 5. Or just a couple other variations, right? -1, 2, 3, -4, 5. Or 1, 2, 1, -2, -3, then 4, 5. So a few different options. So as you can see, there's more than one way to find a sequence that works. But what we're trying to look for is the optimal number of steps. There are other solutions for these numbers that might involve more steps. Okay, so let's take a look at some of the submissions. So this first submission here is by, I think this was by Mackenzie, right? Yeah, Mackenzie.
Yeah.
So what Mackenzie does here in the first portion in that while loop, he basically adds steps into the array while he hasn't reached the target. Or sorry, until he overshoots the target. And then once he overshoots the target, then he goes into the for loop. And what he needs to do is he needs to move backwards to get to the target because he's overshot it. So he moves backwards by basically adding a negative number, the next negative number, and then the next positive number. So let me show you. So for example, this is the output of Mackenzie's code if the target was 11. So the target is 11, he would go all the way up to here. Right, so at this point, he would be up at 15. So he would be at 15. So he's overshot it. Then he needs to go backwards 4 times. So the next 2 lines where he adds 6 and -7, that would be a -1. 8 and -9 is another -1. 10 and -11 is another -1. And 12 and -13 is another -1. So at this point, he's done 4 -1s. Then he's reached the target at 11. So there's a total of 13 steps. So that works. Any thoughts on this, Ronald?
As you can see, this answer does work, but it's not going to be the most optimal. One thing that when you're approaching these problems is what I find really helpful is sometimes to actually write out the steps you take on a piece of paper. So in this, when you rewrite it out, it's very clearly 1, 2, 3, 4, 5. You can see that if you just went back and flipped some of those numbers, and then you can get to the solution without keep adding extra steps into the solution. So I think for this solution, while it is correct, one thing Mackenzie could have done was to go back and to think where the optimizations could occur.
Yeah, exactly. Yeah. So like in this next slide here, we'll show the critique. Instead of going on after 5, once he hit 15, you could have reached 11 by flipping the 2 to a negative. and that would have added to 11 without adding any extra steps. So good point, Ronald. Okay, let's go to the next submission. This one is from Irene.
This one, Irene has a while loop, and we basically continuing to add steps until it is still, while it's still underneath the target that we want, we continue to add steps. Once we break out of that while loop, we check the if condition to see if we hit the target. So if we haven't hit the target yet, then we go into the second while loop, which is on the right. So the second while loop on the right, we check that if it's an odd or even number for the difference. If it's an even number, then we know that we can go back and just flip numbers. If it's not an even number and it's an odd number, we actually bypass that whole if section and we go and continue to add until we get to an even number. So within that if diff modulo 2 block, we see Irene does an interesting choice to break out the logic of where to flip into a helper function called adds to. We didn't include this because it was just extra code, but this breaking it out into a helper function helps keep this main logic nice and easy and clean. After we determine which to flip, we check whether we hit the sum, and then we break out of that.
Awesome. Yeah. So in the next slide here, we actually have an output of a test run of Irene's code. So here the target is 12. So basically she would keep adding numbers into this array until she overshoots 12. So in this case, we're now here at where we just added 5. So now the total here is 15. So then she adds one more, 6. Now the total is 21. It's an odd number, so she adds one more, 7. And then she goes and flips the -7, -1, because at this point, this would be, what was it, 28?
28, yeah.
Yeah, so 28. So 28 minus 12, the difference here is 16. So 16 divided by 2, she needs to take away 8. And so in her adds to, it tells her that we can flip 7 and 1 to reduce this by 8 to get the total. Pretty straightforward code. It works. So this one here was submitted by JE.
JE submission is similar to Irene's, but it chooses to do things a little bit differently. The main differences is that we continue to add steps until it's even. So in that first do while block, we actually already add the sum until it's no longer the difference is no longer 0, or it's not an even, or it's not an odd number. So she chooses to move that logic in the first part, and then in the second part, she chooses to do some interesting calculations. So Irene broke her logic out to determine which steps to flip into a helper function. JE keeps it all in one kind of if-else clause. And also, JE chooses to flip not the n numbers that we saw in Irene's submission, but we actually, she chooses to flip kind of the more middle numbers. So second from the last and second from first. So second and the second from last, yeah.
Yeah, that's this one here, max num -1, I think. So actually, if we go look at JE's output, it's kind of interesting. So where Irene flipped 7 and 1 to take away 8, JE flips 6 and 2. So the second to the last one. So yeah, when you and I were talking about this, Ronald, we were wondering why JE chose to do that. I guess it still works, but it was just different. So actually, okay, JE, if you're listening to this video, please leave a comment and tell us why you did it this way. We're just wondering. I mean, it still works. We just want to know why. And the second thing I noticed is this line here, max num minus minus. I'm not really exactly sure what that does, because all I can see is that it would influence this end condition for the while loop, but I don't think it makes a difference if that line is there or not. So JE or any other viewers, if you have any thoughts on what's the purpose of max num minus minus here, please leave a comment on the video and let us know.
I think the other takeaway, I guess, between these two submissions is that it's not wrong to have different kind of approaches to the same problem. In programming, there's not necessarily one right answer sometimes. So it's good to, I guess, just appreciate the different ways that you can get to the same answer with different methods.
Yes, absolutely. They both gave the same results, and also both of them gave the optimal number of steps. So yeah, just different logic, but it still works. So this one was submitted by Bastian. Okay.
So this one, we both had, when we were going through the submission, we both actually had a bit of, it took us a while to really understand what was going on. So the code here starts off with the quadratic equation to kind of get to the steps up to the target. We think that it's probably not necessarily, and actually Bastian also said as much, that he could probably have dispensed that quadratic equation.
Yes.
But okay, so
just a quick comment there too. So yeah, Bastian, I know we recognize that you know that after you've coded this that it probably was not necessary. So just wondering why you still left it there, because you could have removed it, because now after you've gone through it, then you realize that it's actually not necessary, and you said so in your comments too. So just wondering why you still left it there.
Yeah, I mean, I guess if you already realize it's not necessary, I would say don't be afraid to refactor it or take it out entirely and do it the more optimized way, because at the end of the day, it's what you submit or in a professional project, whatever you commit into GitHub, that's what matters, right? So even if you realize you did it wrong or it's not optimal and you have a better solution, don't be afraid to dump away the old stuff. So we continue on, we do the for loop, and then we continue adding to the steps. So we add an extra step next, and then we check if it's the target. So if we happen to hit the target, then great, we return. Assuming we don't hit the target, then we need to start, adjusting the steps. So you calculate the difference from target here. We check if it's an even number. And then if it's an even number, then we do difference from target divided by 2 minus 1. And then you do a negation of difference from target over 2.
Yeah, basically so just flipping that number there.
Mm-hmm. And so this is in the case where if the difference is even, then you know that you just need to flip half of the difference to get to the right answer, which is good. But I think if it's just a little bit hard to read what it's doing there without understanding it. But we can continue. So if the difference is not even, then we continue adding steps. And then you do the same thing and you check if it's even again. So if it's even again, then you know that you can just flip half the target again and return. So finally, if it's still odd, then you know that you can just flip the step that you just added to make it to change it from an odd to an even number. And then you also figure out
he adds another step, but he adds a negative step.
Oh yes, sorry. So he adds an extra step, but it's a negative step, so it turns it into an even. And then you do the calculate the difference from the target divided by 2 again, and you flip whatever is half from the difference still. I mean, as you can tell, I mean, I as we're walking through the code, it's still very hard to kind of step through it. So
Yeah.
go
The
ahead.
one good thing is that he does have a lot of comments, but so the kudos to that, having all the comments. But what makes it hard still is that even in spite of all the comments, it was still hard to read because the variable names that you use is not 100% descriptive of what that variable is used for. So the difference from target here, when you first define difference from target as total value minus target, so that seems to make sense. But later on, I don't know, does it still have the same value when you're subtracting that step there? Does it still have the same meaning? Another thing that was confusing is if you see the steps here, you're adding a step here, but then later on you're adding a negative step plus one. So because the semantics are shifting, it makes it harder to understand. I mean, it still works. The code still works, right? Like when we run your code, this is the output that we get, and it works. Well, actually, it is the wrong output. It's a -1 and a -7. So it still works, but it's just hard to understand. And because it's hard to understand, that also means that it's hard to maintain. So if you needed to make a change to the code, it'll be harder to do that.
Like I guess if Bastian, if you're watching this, if you're looking at your own code, a week from now, I guess whenever you watch this video, it would be a couple of days since you probably looked at this code. Do you still remember every single thing in the if-else blocks, right? And if you yourself are having trouble remembering what each kind of thing is doing, then can you imagine 6 months from now, or if this was your game of apps project, let's say you wrote some code at the beginning and then 8 weeks later towards the end something is not working, can you still remember what you were doing 8 weeks ago? Probably not. So it's just something to keep in mind. When you're doing writing code, if it's hard to read, then it's hard for yourself later to debug as well.
Yeah.
I guess one thing we could touch on is that some of the code with the repeating, checking if the steps difference from target and things. I mean, you can see it's a lot of repeating code. Maybe try to refactor it into like a while or a for loop or something like that, where you're not, walking through the same code, but you're copying it.
Yeah. So Bastian, hopefully these are make sense, and hopefully it helps you. I mean, it's still right, and it still gives the optimal code. The only critique here is that it's harder to understand than some of the others that we've looked at so far, and also harder for you to maintain probably. Okay, let's look at this submission. This one was submitted by Arthur.
For this one, it starts off pretty regular. We actually start off with the for loop and we overshoot it by 1. And we do a quick check to see if, after we finish the for loop, we do a quick check to see if we're over the target. And then here is where it kind of starts going off the rails a little bit. In that, so you can see that Arthur defined a difference is odd, -1. So normally, if you're setting a variable like that, a reasonable assumption would be that it's a Boolean, so 0 or 1. Except in this case, Arthur actually, it's a triple state variable, so -1, 0, or 1. And the reason why he does that is because he needs to check, and now we're over on the switch statement now on the first case. So case -1. So if the target on the left-hand side there doesn't fall in any of the if-else clauses, then the difference is odd remains as -1. So that's how he determines whether we've hit the target right away. So actually, that's kind of not the best way, I would say, to do this, because you could have easily moved that check right after the for loop into a separate if-else statement. Yeah. So if you do that, that's actually a lot more clearer, and you're not overloading that variable, which is a Boolean or a reasonable assumption to be a Boolean.
Yeah, I mean, when you say difference is odd, it's either is odd or it's not odd, right?
Yeah, and I think more importantly that this when other programmers work on this, they're going to expect that it's a 0 or 1, right? They're not going to necessarily expect a -1 or other variable number to come up. So just something to keep in mind. Okay, so then we can continue into case 1. So case 1 is basically checking if it's a...
Sorry, my scribble there is supposed to be odd.
Yeah. So case 1 checks if the difference is odd. And so if it is odd, then we continue adding steps until we get to even. And then if we can hit the target as a result of all the shifting, then we can simply break out and return. Okay. And if it doesn't, then we fall through to the case 0.
Yeah, this is the even case.
Yeah. So here we do the shifting and we find the difference divided by 2 and we set that as -1. So pretty similar to all the other solutions. And then step 4, Arthur decides to actually check if we hit the target. And actually this is pretty redundant because if you can see whether or not we hit the target, it doesn't matter because at the end of the day, you're going to be returning the steps. So maybe he put this here for debugging or he left it in for debugging, but actually you could just take it out and it wouldn't affect the solution at all.
Yeah.
If it's wrong, then you're going to return a wrong answer.
Yeah, that's right. As a debugging code, I think that would be very useful, right? Because before you return, you want to make sure that your calculation is right. Mm-hmm. But then when you're submitting this for production, we don't need it. Because like you said, if sum equals target, you print, yay, you got it. But what if it's not? You still return it anyway.
Yeah. So the one comment here, other than the overloading the Boolean variable, is that the use of the fall through, while it's valid, actually produces relatively dangerous code in that it might have unintended consequences or unexpected behavior because of that fall through. So in general, we try to avoid using fall through unless there's a really good reason to do so.
Yeah, that's right. So basically with the fall through, what you're doing is you have 2 cases, and what you're saying is that one case is a complete subset of another case. Mm-hmm. So you have a case that is a superset of another case, which is a subset. And so that's what you're using this fall through for. And it's okay to organize your logic and your algorithm that way, where one is a complete subset of another case. But maybe instead of putting it in a switch statement like that, you could have maybe put the sub case in its own function, and then you call it twice, for one for each of the 2 cases. In one case, you just call it directly. In the other case, for the superset, you would execute some code before you call that sub case. Mm-hmm. It's just a bit easier to read, a bit easier to understand. This fall through of switch statements is actually an inherited semantics by Java from C and C++. And the reason C had it is because in assembly, it's very common for programmers to program this way. They have go-tos and jumps. You would jump right into a loop, jump out of a loop. So, and that's called spaghetti code, right? So although it works, it makes it very hard to reason, and makes it very hard to walk through.
That actually reminds me of a big bug. This was probably maybe 3 to 5 years ago, where there was a big go-to bug, where somewhere in production code, I have to look this up, but we can post a link if I can manage to find it. But basically, somewhere someone put a go-to, and either they forgot about it or they left it, and it actually caused a huge bug. And I think I want to say it's an Apple software. Do you remember?
No, I don't remember.
Ring a bell? Okay. But if we can find the resources, we can link it. But yeah, this kind of speaks to the unpredictable nature of using kind of the fall throughs or using a go-to. You just kind of, sometimes you just either forget or you don't know where the code is going, and the consequences are unintended.
Yeah. So if we look at your output here, so it does work. So again, this is the optimal solution. So it does work. Again, similar to the comment in the previous submission, it does work. It's just a little, the code could be structured better. So some of the things that Ronald and I talked about are things to consider. Let's take a look at the next submission. This one here is submitted by Eric. But actually, Eric submitted this. Oscar and Jason had something that looks very similar as well. So a very similar algorithm.
Let's dive into it. So for the first for loop, we're checking if both the sum is less than the target and the sum is a even number and is not equal to the target, which is also an even number.
Or actually, I think it's
the
more,
remainder. Sorry.
Yeah, so it's checking to see that the sum and the target neither both of them are even or both of them are odd. So they can't be both even and they can't be both odd. So that means one of them has to be even and the other one has to be odd. That's what this logic says. But you see how hard it was for us to explain that? So that means that this logic is pretty convoluted, right? Basically what you're doing, if both the sum and the target are even, that means that the difference is even. If both of them are odd, the difference is also even. But if one is even and the other is odd, that means the difference is odd. So what you're actually checking for is that you want the difference to be odd, right? So if you can boil it down that way, then it's a lot easier, rather than forcing the reader to understand what does it mean when the sum is even and the target is even, or the sum is odd and the target is odd. So rather than forcing the reader to kind of work through that, just make it simple. You're looking for the situation where the sum is the sum minus the target, which is the difference, is odd, because that's basically what you're looking for.
And then, so after that, we check if the sum is greater than the target. And if it is, then because of the earlier check with the sum and the target is both even or both odd, then we can determine that if the sum is greater than the target, then we can immediately go and do the calculation to see what's the half of the difference and find the flipped number to flip right away.
So here, semi-difference should be, so sum minus target is already even, so that we know that we can divide it by 2 with no remainder.
Mm-hmm.
And so then
we can immediately find the step.
Yes, to flip, yeah.
To flip, yeah. So in the case where the half difference, half of the difference is greater than the steps of the size, then that means we need to start flipping multiple numbers. So that's where the else if clause comes in. And this is the second part where the logic is pretty unique, such that, for a couple people without, I guess, collaborating, it would be pretty hard to come up with that exact same answer. You can see with the previous submissions, I think Irene chose 7 and 1 to flip, and Jade chose 6 and 2. So if we take a look at the output for these 3 submissions, they actually chose 3 and 5 to flip. So again, kind of like earlier, Eric, Jason, Oscar, if you're watching this, leave a comment in the section below. Why negative 3 and 5?
Yeah.
I mean, you got the right answer, yeah. But why specifically those numbers? We're just kind of curious.
Right, just curious. I mean, And I guess given that the three of you kind of came up with submitted a solution that looks very that is based on a very similar algorithm, I guess it's very possible that the three of you work together on this, and that's fine. It's okay to collaborate and work together. I just hope that it's not the case where one person did all the work and the other two just kind of just basically relied on that work, right? Because like Ronald said, this solution is pretty unique in that there are some things here that are so unique that, like, this representation here is quite unique, and then these formulas here for calculating which numbers to flip is pretty unique too, right?
Mm-hmm. I guess it's okay to collaborate, like Roland said, but I think what's important is what did you learn, right? We're running these for your benefit, and if you're just if you're not learning from them, then there's really no point for you to attempt, right? Because at the end of the day, it's about your future and really becoming a better dev through practice.
All right, so then now we come to our last submission. This last submission is submitted by William.
So William chose to do this entirely in one while loop. So everything just keeps looping until we hit one of the conditions that returns. So here in the first if, we check if the sum is less than the target, or if the sum minus the target divided modulo 2 is not equal to 0. So he's just checking if it's odd. And he knows that because if the difference is odd, then you can't get an answer. So he continues, and then if you hit the target, then great, we return. So the next section with the else is where most of the magic happens. And here we swap the first location, basically the last number. You flip the last number to check. I think the code continues, right?
Yes, the code continues. Yeah.
Yeah. So you first flip the last digit, and then
I think. Scenario here is where
you just need to flip one.
Yeah, you just need
digit.
To flip one. Yeah, that's right.
Yeah.
Because the difference, the amount that he needs to flip is less than the maximum number that we've already added. So then we just have one digit that we need to flip.
Mm-hmm. And then the else case is if we need to flip multiple digits.
Yeah. So it's 2 digits. Because the amount that he needs to flip is greater than the biggest number that we've just added. So you need to flip at least 2 digits. Now he had a comment here that says, would there be a situation where you might require to flip more than 2 numbers? So do you have to flip 3 numbers? I'm not sure if you need, if that's the case, but that's a good question. I mean, so far in all the data sets that we've run, we haven't had a need to flip more than 2. But William correctly points out that if you need to flip more than two, then this code won't work.
When we went back to actually look at the problem set that we provided, it was not necessary to flip more than 2 numbers. So again, if you find a target number that requires more than 2 flips, leave it in the comment section below. And we'll rerun this exercise to see who can come up with the best solution.
Because we can't definitively say that you won't require more than 2 because we haven't proved it mathematically and we haven't run through all possible data sets. But actually, some of the previous algorithms, I think like Irene's algorithm, that function that she broke out, that if it requires 3 numbers to get to the difference, her algorithm will actually return 3.
I guess just in general, just kind of projecting forward beyond this problem, I think know your, problem set. And for something like this, where you're doing a math kind of thing where, maybe you can mathematically prove that, it's not possible to have 3 flips, then great. But I guess it's never bad to account for those potential edge cases, even if it means, there might be more flips that are less optimal. At least your code is more resilient and less brittle when it hits those kind of potential edge cases.
Okay, so I think that's it for today. If this has been helpful, please give us a like on this video. And please feel free to watch any of the videos that we have on our channel too. So stay tuned. We have another challenge coming up this week, but that'll be in a separate video. So please watch out for that. Okay. Thank you, Ronald. And then thank you, everyone.